Okay, so get this, listeners. We're diving into the theory of computation today. But hold on, before you hit that skip button, it's not just about ones and zeros, you know? It's about peeking into the core of what computers can do, and maybe even more importantly, what they just can't.
Yeah, it gets pretty deep.
It does. And our source material, it's a straight up university level course on this stuff.
Oh, wow.
But don't worry, we're going to skip the boring lectures and go for the mind blowing stuff, the stuff that really makes you think. Ready to unlock some computational secrets.
I am, definitely. The theory of computation, it gets pretty wild, but there are some key ideas, some real core concepts that'll change how you think about computers and even just problem solving in general.
Absolutely. This course, it breaks things down into three big areas, kind of like the pillars of computation. We've got complexity theory, then there's computability theory, and finally, automata theory. Now, complexity theory. That one always makes me think of those brain teaser puzzles that take, forever to solve. Am I on the right track there?
You are. You are. It's all about figuring out why some problems, they're a breeze for computers to handle, and then others, they turn into these computational nightmares.
I see.
Right, like sorting numbers. A computer does that in a blink.
Yeah.
But try creating a university course schedule where nothing overlaps. Suddenly your computer is sweating. Complexity theory tries to measure and understand that computational effort.
Okay, so it's like the difference between, I don't know, finding a book on a shelf versus solving a Rubik's Cube, but blindfolded. Some tasks are just more complex, even for a computer, right?
Yeah.
Now, computability theory, that one sounds even more intense. Are we going to figure out if computers can, become sentient or something?
Not quite sentient, no, but it dives into something just as mind-blowing. Are there problems computers can never solve, no matter how powerful we make them?
Okay, now that is fascinating.
And the answer is?
Yes.
Seriously. Seriously. There are problems that are undecidable, meaning no algorithm, no matter how clever, no computer, no matter how powerful, can guarantee a correct solution every time.
Wait, hold on. So even with all the processing power we can dream up, there are still hard limits to what computers can figure out. That's both amazing and kind of unsettling, isn't it? Give me an example. What kind of problem is so mind-boggling that even a supercomputer throws its hands up?
All right, imagine this. You're trying to write a program that can look at any other program and tell you for sure, without a doubt, whether that program will eventually finish or get stuck in an infinite loop, just running forever.
Oh, that's tricky.
It's impossible, actually. It's called the halting problem, and it's one of the classic examples of an undecidable problem.
Wow. Okay, so even in the world of computation, there are mysteries we may never solve. But I guess that's part of what makes it so fascinating, right? Now we've talked about complexity, we've touched on computability. What about that third pillar automata theory? What's that all about?
Right, so think of automata theory as the study of different kinds of computational machines and what they can and can't do. But these aren't physical machines like your laptop. More like abstract models that help us understand the underlying principles of computation itself.
Okay, so kind of like blueprints for different computer brains, right? I've heard of things like finite automata and Turing machines.
Okay.
Are those what we're talking about here?
Exactly. We'll dig deeper into those in a bit. But picture this, a finite automaton. It's like a simple machine with a limited set of states and a very basic way of processing information. Like, think of a vending machine. It has a few options, and it reacts based on what you put in.
Right. You put in the right coins, you get your snack. Wrong coins, nothing happens. Simple, but effective.
Exactly.
So then where do these Turing machines fit in? They sound way more complex.
They are. Imagine a finite automaton, but instead of limited states, it has this unlimited memory tape, like a really, really long scroll. It can store information there and change it. That makes it ridiculously powerful. In theory, a Turing machine can simulate any computational process you can imagine.
Hold on, any computational process. So we're saying theoretically a Turing machine is like the ultimate computational blueprint. That's a bold claim.
It is. It's one of the foundational concepts in computer science. It's even got a fancy name, the Church-Turing thesis. It basically proposes that anything that can be solved algorithmically can be solved by a Turing machine. So, yeah. Kind of a big deal.
Okay, my mind is officially blown. So we've got these three pillars: complexity, computability, and automata. And already I'm seeing how they're all kind of intertwined. But how does all this abstract stuff connect back to the real world? What practical implications does it have?
Well, complexity theory. That has huge implications for things like cryptography, protecting our digital information. Understanding those problems that are hard for computers to solve, it's essential for designing secure encryption algorithms.
So the tougher the problem, the harder it is to crack the code, right?
Yeah,
That makes sense. In a world where data security is everything, that's got to be crucial.
absolutely.
But beyond cryptography, are there other ways complexity theory shapes our world?
Oh, it's way more widespread than you think. Complexity theory pops up in optimizing delivery routes, managing logistics, even making everyday decisions. Think about planning a trip. You're basically tackling a complex problem, minimizing travel time, maximizing sightseeing, all within a certain budget. Understanding complexity, it helps us approach these kinds of challenges more strategically.
Huh. Never thought of it that way. That's a great point. So let's circle back to computability for a sec. We talked about how some problems are just impossible for computers to solve, no matter what. But how did we even figure that out? It seems mind-boggling to even prove that.
Yeah, it was groundbreaking work.
Yeah.
Back in the 1930s, you had mathematicians like Gödel, Turing, and Church. They were wrestling with the very foundations of math and logic.
Deep stuff.
And they discovered, through some incredible work, that there are inherent limits to what formal systems can prove or compute.
So they were like the pioneers of figuring out what's computable and what's not. They laid the groundwork for our understanding of computation.
Exactly. And get this, their work. It was pivotal in developing the computers we use today.
Wow.
Even though they were focused on limits, they were also defining the boundaries of what was possible, which in turn led to incredible advancements in computer science.
So by identifying the can'ts, they unlocked the cans. Amazing. Now, I know the source material dives into some of the nitty-gritty math of the theory of computation. Are we about to go full-on math class here?
Don't worry, we won't be proving any theorems or anything.
Okay, good.
But there are a few key mathematical concepts that are worth mentioning, because they provide the language and the tools we use to analyze and really understand computational problems. They're like the building blocks of computational thinking.
All right, let's break it down. What kind of math concepts are we talking about here?
Okay, we've got sets, sequences and tuples, functions and relations, graphs, strings and languages, and finally, Boolean logic.
Some of those sound a little intimidating.
They might sound intimidating, but I promise they're actually pretty intuitive. Once you grasp the basics, it's like a light bulb moment.
Okay, I'm ready. Walk me through it. What are sets, sequences, and tuples all about?
Okay, think of sets as just collections of unique objects. Your grocery list, that's a set of ingredients. But a recipe, with its specific order of steps, that's a sequence. And a tuple, it's like a fixed-length list. Think of coordinates on a map, latitude, longitude, altitude, that's a three-tuple.
I like those examples, very clear. So sets are about collections, sequences are about order, and tuples are those fixed lists.
Got it. What about functions and relations? Those always felt a bit abstract to me back in school.
They can be, but they're essential for understanding how things work, especially in computation. A function, think of it like a little machine. It takes an input, processes it based on a rule, and spits out an output.
Yeah.
The absolute value function, for instance. You put in any number, positive or negative, and it gives you the positive version of that number. Always.
Like the addition function. Two numbers go in, their sum comes out. So functions are all about these predictable input-output relationships. What about relations? How do they differ?
Think of a relation like a statement that can be true or false, depending on what you put in, like the less than relation. Is 5 less than 10? True. It's less than 5. False. Relations help us describe how things compare to each other.
And I bet they're used all the time in computer programs to make decisions and comparisons. What's next? Okay, we've got graphs. These are incredibly useful for visualizing data and relationships. Think of cities connected by highways. That's a graph. Or the network of friends on social media. Also a graph. They help us see connections and analyze complex systems.
Graphs are definitely everywhere. Okay, how about strings and languages? Those sound pretty straightforward.
They are. A string is basically a sequence of symbols from an alphabet, like the letters in a word or the digits in a binary number. And languages, they're sets of strings that follow specific rules.
So the English language is a set of words formed using the English alphabet. And a programming language has its own set of rules for creating valid code. Makes sense.
Exactly. Understanding languages and how they're structured is super important for designing things like compilers and interpreters. The tools that translate code humans can read into instructions a computer can understand. Now, last but not least, are you ready for Boolean logic?
Hit me with it.
Boolean logic. This is where we get to the very heart of how computers think at the most fundamental level.
Boolean logic. Does that have something to do with true and false values? I vaguely remember something from a computer science class ages ago.
You got it. Boolean logic is all about working with true and false. Usually they're represented as ones and zeros in a computer, It uses logical operations like not, andy, and or to build more complex expressions.
Ah, so it's like the basic language of digital circuits, of computer programs. Just using true and false, you can build incredibly complex logic and computations. That's pretty amazing.
It is. It's the basis for everything from simple calculations to, well, artificial intelligence.
Wow. We have covered a lot of ground, the three pillars of the theory of computation, those core mathematical concepts.
Hmm.
It's amazing to see how it all connects. I'm already looking at the world of computation in a whole new way.
Yeah, we're just getting started.
I can't wait. Stick with us, folks. We'll be right back to dive even deeper into automata theory and those fascinating computational models. We're about to unlock some serious secrets of the computational universe. Welcome back to our deep dive. Before the break, we were talking about those computational models, finite automata, and Turing machines. I'm ready to learn more.
Yeah, they're really fascinating, kind of like simplified blueprints of computation.
Blueprints, okay.
They help us understand those essential elements of how computers process information, at their core.
Okay, so let's start with those finite automata. You mentioned they're kind of like vending machines. Can you break that down a bit more for me? Like, how do they actually work?
All right, so imagine a simple machine.
Okay.
It's got a limited set of states, like waiting for coins, dispensing a snack,
Yeah.
or maybe even out of order.
Yeah.
It also has a set of inputs it can receive, different coins, maybe buttons being pressed. And based on its current state and the input it gets, the machine transitions to a new state. And it might produce an output, like dispensing your snack or giving you change.
So if you put in the wrong coin, it might just stay in that waiting for coins state and not give you anything.
Exactly. That's a finite automaton in a nutshell. A system with limited memory and a set of rules for how it responds to different inputs. You'd be surprised how powerful they are for modeling simple processes and recognizing patterns.
So besides vending machines, where else do we see these finite automata in action?
Oh, they're everywhere. Think about spell checkers. They use finite automata to flag those misspelled words, or those lexical analyzers and compilers, breaking down your code into meaningful chunks. Even simple AI agents, like those basic chatbots that answer questions, they can be modeled using finite automata.
Wow, so much computational power packed into such a simple model. All right, let's move on to those Turing machines. We talked about how they have like unlimited memory, right? Which makes them theoretically capable of simulating any computational process. But how does that even work?
Okay, picture this. It's like a finite automaton, but instead of having a limited number of states, it's got this infinitely long tape. You can read from it and write to it. This tape acts as its memory, so it can store and manipulate an unlimited amount of information.
So it's like a finite automaton with a superpower, unlimited storage space.
Exactly. The Turing machine, it moves back and forth along this tape, reading and writing symbols based on its current state and the symbols it encounters. And this simple mechanism, believe it or not, it allows it to perform incredibly complex computations.
That's pretty amazing. Something so basic can be so powerful. But you mentioned earlier that Turing machines are more of a theoretical concept. Why don't we just build computers based on them directly?
Good question. While they're incredibly powerful in theory, they're not very practical for real-world computing. That infinite tape, for instance, we can't actually build a machine with infinite storage.
Right, of course. So they're more like a gold standard then for understanding what's computationally possible, not a blueprint for actual computer design.
Exactly. They provide a framework for analyzing algorithms, for proving limitations, even for exploring the very nature of computation itself. Like, they help us answer questions like, can this problem even be solved by a computer? Or, what's the most efficient way to solve this problem?
That makes a lot of sense. It's like having a yardstick to measure the complexity of problems and the capabilities of different models. Now, we've talked a lot about the power of Turing machines, but we also keep mentioning limitations. If they can theoretically compute anything, what are these limitations?
Well, the limitations come from computability theory. Remember, we discussed how it explores the boundaries of what computers can and cannot do. Think back to the halting problem we talked about.
Right, the one where you're trying to predict if a program will ever finish running.
No computer, not even a Turing machine, can solve that problem definitively.
So even with all the power of a Turing machine, we still hit those fundamental limits of what's computable.
Precisely. And that's where Alan Turing's genius really shines. He developed this powerful proof technique called diagonalization.
Diagonalization.
It shows that some problems are just inherently undecidable.
Diagonalization. Can you give me like a simple explanation for how that works?
All right, imagine you have a list of all possible Turing machines. And you want to create a problem that no Turing machine on that list can solve. Diagonalization is like creating a rebel problem. It contradicts what each Turing machine on the list would do.
So like a custom-made puzzle designed to stump every possible Turing machine.
Exactly. And because Turing machines, they represent all possible algorithms, this proves that those problems, they're undecidable by any computational means. It's a pretty wild concept.
It really is. So even with the theoretical power of Turing machines, we run into these hard limits of computation. But understanding those limits, that's got to be just as important as understanding the possibilities, right?
Oh, absolutely. Knowing what you can't do is crucial. It helps us avoid wasting time and resources on impossible problems. And it guides us towards finding solutions for those problems that are actually solvable.
It's a good lesson. Now, before we wrap up automata theory, I want to circle back to those real-world connections we talked about earlier. You mentioned how finite automata are used in spell checkers and compilers. What about Turing machines? Do they have applications beyond, theoretical computer science?
While Turing machines are primarily theoretical tools, their impact is felt throughout computer science and beyond. Their ability to simulate any computational process, it helps us understand the limits of computation in fields like AI, cryptography, even theoretical physics.
So they're like the ultimate benchmark for what's computationally possible, which has implications for all sorts of fields.
Exactly. And even though we can't build a physical Turing machine, the concepts they embody, they're deeply connected to how we design algorithms, how we analyze complexity, how we push the boundaries of what computers can achieve.
A pretty amazing legacy for a theoretical model. Okay, let's take a step back and recap what we've learned about automata theory.
So we started by exploring those finite automata, simple but powerful machines that can model a surprising range of processes. Then we delved into the world of Turing machines, those theoretical powerhouses capable of simulating any computational process we can imagine.
And we saw how understanding these models, especially Turing machines, helps us analyze those algorithms, prove those limitations, and really explore the nature of what's computable and what's not.
We also discussed how these concepts, which seem abstract, have real-world implications. They shape how we design secure systems, how we develop efficient algorithms, even how we approach complex problems in our everyday lives.
It's been a whirlwind tour of automata theory. I'm seeing the world of computation in a whole new light now.
And we're not done yet. There's still so much more to uncover about the theory of computation and its implications.
I'm ready for more. Stay tuned, folks. We'll be back in a jiffy to wrap up our deep dive and leave you with some thought-provoking questions to ponder. We're back for the final part of our deep dive into the theory of computation. We've covered so much ground: complexity, computability, those computational models, but there's one thing that keeps coming back to me. If there are limits to what computers can solve, does that mean there are limits to what we can know?
That's a big question. And the source material kind of wrestled with that too. It's like, by figuring out what's computable, we're also maybe hitting the edges of our own understanding.
So it's not just about the computers, but what those computational limits tell us about knowledge itself. That's deep.
It is. Think about this. If we can't even describe a computational process to get to a certain piece of knowledge, what does that say about whether that knowledge is even attainable at all?
Okay, so there might be knowledge out there that's just beyond the reach of any algorithm or any computer, no matter what we come up with.
Exactly. And it makes you think about those parts of human intelligence that seem to go beyond pure computation. Consciousness, creativity, intuition. Can algorithms ever capture those? Or are there just fundamental differences between how we think and how computers think?
It really does make you wonder if there are some mysteries that even the most powerful computer will never be able to crack.
It's a humbling thought, right? That even with all our technology, there might be realms of knowledge and understanding that are just beyond our computational grasp.
Right, so we've explored those computational superpowers, dived into the limitations, even touched on some pretty philosophical stuff. But what does this all mean for us, the everyday users of technology?
Well, it helps us appreciate the complexity of the systems we use all the time. Our phones, laptops, the internet. They're all built on this intricate web of computational theory.
Makes sense.
Understanding those foundations, it gives us a better grasp of both what's possible and what's just not possible with the technology we rely on.
So it's like peeking behind the curtain and seeing the machinery that makes it all work. We become more informed users.
Exactly. More critical thinkers, too.
Yeah.
About the technology that shapes our world.
Now, before we wrap up our deep dive completely, I want to leave our listeners with one last thought to chew on. Remember how we talked about those problems that are provably impossible for computers to solve? What does that mean for fields like artificial intelligence, where the goal is to create machines that can think like humans, maybe even surpass us?
Another great question. If there are fundamental limits to computation, does that mean there are limits to AI too? Are there parts of human intelligence, like those things we mentioned earlier, that algorithms just can't touch? It's a question researchers and philosophers will be debating for years to come.
It really shows you how powerful the theory of computation is, that it sparks these deep questions about ourselves, our technology, even the nature of knowledge itself.
So the next time you're using your favorite tech, remember, beneath those sleek designs and intuitive interfaces, there's a world of math, of deep philosophical questions just waiting to be explored.
Absolutely. We've journeyed through the complexities of computation, we've uncovered hidden powers and surprising limitations of computers, and hopefully this deep dive has sparked a bit of curiosity in you about the intricate dance of logic and computation that really shapes our world. Keep those questions coming, keep exploring, and until next time, happy computing.